Hey y'all, we're going to look at a couple examples here about conditional probability. So this is where probability can get a little bit tricky, so I want to record a couple examples that you guys can look back at. So conditional probability is denoted like this, A and then this pole thing, which means given. So A given that B has happened. So when we're calculating conditional probability, we're going to look for what is the probability of an event happening given that we already know something else has happened. So let's look at a couple of examples of what this might look like. We'll do two examples. The first one's with a two-way table. It is a little more straightforward from what we've seen before. And then we'll look at one that's a little more difficult. We'll use a tree diagram to think through that one. Okay, so the setup for this one is we're looking at a Diamondbacks policy, the Arizona Diamondbacks, where you get 3 free tacos from Taco Bell if the Diamondbacks score more than 6 runs in their game. If you've ever been to a sporting event, a major league sporting event, you've seen these kinds of deals with some free fast food. All right, so it says the Diamondbacks won 41 out of their 81 home games and gave away free tacos in 30 of the 81 home games. In 26 of those games, the Diamondbacks won and gave out free tacos. Okay, so we've got two events. We've got the Diamondbacks win a game, so that's event W, and T is tacos. So the first thing I want to do is organize my data. You could do this with a Venn diagram, but I'm going to go with a two-way table here. So we've got they win the game, or they not win the game. Remember, this C means the complement, means not that. So win, not win. Okay, we don't want to avoid using like W and L because we don't want two symbols to basically mean the same thing. Okay, and then we've got tacos and not tacos. All right, there's my hideous two-way table. So it said in 26 of the games, we both won the game and got tacos. And it said that they won 41 of their games. There were 81 games, 81 home games. So if they won 41, that means they lost 40. Okay, and it says they got free tacos in 30 of those 81 games. So that's 30 tacos, which makes 51 not tacos for that to add up to 81. Okay, so that's the information we were given. Well, I've added this and this just from simple subtraction. We should be able to fill in the rest the same way. So if this adds up to 30, we need a 4 here. We need a 15 here, and then 36. All right, so this two-way table is going to help us answer some probability questions. All right, what's the probability that the Diamondbacks win or there are free tacos? So remember our general addition rule. Probability of win or tacos. Remember that U symbol, the union, means or. So probability of two things happening, one thing or the other thing. We've got the probability of the first event plus the probability of the second event. But we want to be careful because winning the game and getting free tacos are not mutually exclusive. Those two things can happen together. Indeed, they did 26 times. So we need to subtract the overlap because those 26 games are being counted in the 30 tacos and in the 41 wins. We don't want to count them twice, so we'll subtract that off once. Okay, so probability that they win is 41 out of 81. Didn't plan very well for my space here, but that's okay. Probability of tacos, 30 out of 81. And we want to subtract the 26 that got counted twice here. All right, so that's going to be 45 over 81, which, according to my answer key, is about 55%, about 0.556. 0.55, make this a little better. All right, so about 56% of the time, we either won the game or got free tacos, which sounds like a good day at the ballpark either way. All right, the next one says find the probability that the Diamondbacks win given that there are free tacos. Now, this is the first time we've seen a given condition for our probability, and we don't really need any new formulas or anything to figure this out because we've got this two-way table in front of us that'll help us answer this. So, it says what's the probability that the Diamondbacks are going to get a win if we know that there's already free tacos. So maybe we go to the bathroom, we didn't get to watch the 9th inning, but we see people leaving with their Taco Bell coupons ready to get their free tacos. So what's the probability that the Diamondbacks had just won that game if we know there are free tacos? Okay, so we would look at this row right here where we see, okay, there were 30 games where free tacos were given out. 26 out of those 30 were a win. So the probability that we will win given that tacos, free tacos, is 26 out of the 30. All right, there were 30 games where free tacos happened. 26 of those were wins. Now, we can make this a little bit prettier. We can say win given that taco. Okay, this poll means a given condition. And we could say the same thing, 26 out of 30, which is about 87%, 0.87. Okay, so again here we knew that there were free tacos, so we only care about these 30 games in the free taco row. Let's look at the next one. Find the probability that there are free tacos given that the Diamondbacks won the game. So flipping it around now we're looking for the probability that tacos, given that, win. Okay, so this time we know they won the game. Okay, so maybe we are in the bathroom and we missed the whole game this time because we had some bathroom problems. But we do hear everyone cheering really loud at the end of the game, so we know the Diamondbacks won, but we don't know how many points they scored or how many runs they scored, so we don't know if we got those free tacos or not. Which, given our bathroom situation, maybe it's good that we don't get those tacos. Okay, so we want to know what's the probability that there are free tacos given that we know the Diamondbacks have won that game. So this time we're looking at this column. We only care about wins, right? Given that the Diamondbacks win, we only are going to focus on games they won. There were 41 of those games, and in those 41 games, 26 of them were free taco games. So our probability is simply 26 over 41, which my cheat sheet tells me is about 0.63. Okay, so this is what conditional probability means. Looking at what's the probability that something's happened given a certain condition, right? Given a certain restraint that we're going to look at. This was a really sort of baseline way to start doing this. The next one's going to be a little more complex. We're going to think about a different way to represent this idea, and we'll look at a formula that will allow us to calculate this even if we don't have the raw data like we did with our two-way table. So this was sort of a baseline way to approach this problem, but we've just discovered how to find a conditional probability. So the probability that tacos would happen, given that we knew a win happened, what we did is we looked at, okay, let's look at how many games were wins. So what's the probability of a win? Well, the probability of a win was 41, right? 41 out of the 81. We're not going to worry about that. Okay, looked at all the possible outcomes where there was a win. And then we looked at, well, of those wins, which ones were also tacos? Probability of tacos and wins. So this is the formula for conditional probability. The probability that A given B is equal to the probability of A and B divided by the probability of B. Okay, we're going to need this in just a second, and I'm going to make this A and B because that's sort of the general way to write it. Okie dokie. All right, so let's take a look at this next one. This time we're going to use a different way to visualize our data. Before we did a two-way table, we could have done a Venn diagram. Here we're going to use a tree diagram, which is really, really useful for conditional probability, where we have events happening sequentially. Okay, so it says Shannon hits the snooze bar on her alarm clock 60% of school days. If she doesn't hit the snooze bar, there's a 90% chance, 0.9 probability, that she makes it to class on time. However, if she hits the snooze bar, there's only a 0.7 probability that she makes it to class on time. Okay, so let's map out these events with something called a tree diagram. And these are really intuitive. I like these a lot. They can be a little confusing at first, but once you get used to them, they're a super useful tool for looking at probabilities. Okay, so the first thing that can happen, Shannon hears her alarm clock. She can either snooze or not. So we have the first branching realities here. Either she snoozes or she no snoozes. All right, so that said there was a 60% chance that she snows. So 0.6 for snows. There's a 40% chance that she do not snows. Okay, so that's our first branch on our tree diagram, right? We start from this singularity here, and we can branch off into two possibilities. She either snoozes or nah. Okay, and then if she snoozes, okay, so let's start with this. If she doesn't snooze, there's a 90% chance that she gets to class on time. So in the no snooze version of reality, there's a 90% chance that she's on time, which means there's a 10% chance that she's late. The face isn't covering this up, is it? No, we're good. All right, and if she does snooze, what's going to happen? So it says if she does snooze, there's a 70% chance that she makes it to class on time. So only a 70% chance that she's on time, which means there's a 30% chance that she's late. So notice that I was able to fill in those missing pieces. They didn't tell us this, they didn't tell us this. I was able to fill those in because every branch has to add up to 100%. So every split adds up to 100%. 0.6 and 0.4, 0.9 and 0.10, 0.7 and 0.3 all add up to 1 or 100%. Okay, so we've got our tree diagram mapped out here. I'm going to throw this in a box real quick. We don't have to put it in a box, I just don't want it to get mixed up with that formula up there. All right, so when we're looking at a tree diagram, again, each branch has to add up to 100%. And then our second branches are the conditional probabilities, right? There's a 70% chance that she gets to school on time, given that she has snoozed. There's a 90% chance she gets to school on time, given that she has not snoozed. Okay, so we already know our conditional probabilities, but we're going to look at some other stuff. So the first question we're going to look at says, on a randomly chosen day, what's the probability that Shannon is late? So there's two different ways she could be late. She could be late after having snoozed, or she could be late after having no snoozed. So we've got to calculate what's the probability of both of these things happening. So let's take a look. So probability of being late is going to be equal to the probability of snooze and late plus the probability of no snooze and late. So let's find those probabilities. So what's the probability that she snoozed and was late? So when you're using a tree diagram and you want to know probabilities down the branch, all you have to do is multiply those, right? The probability that she snoozed and was late. Well, we said that 60% of the time she snoozed, and then 30% of that 60% she was late. So we just need to take the 60% of days, multiply by 30% of those, and we get 18%. Okay, we can do the same thing for no snooze and late. So probability of no snooze and late. Well, if she's no snoozes on 40% of days, and then of those 40% of days, she's late 10% of the time, well, then that means 4% of all days she is late and did not snooze. Okay, let me go through that again. So again, she does not snooze 40% of days. and then she's late 10% of that 40%. 10% of 40% is 4%. So we're going to add that to this, and we get our final answer. She is late 22% of days. All right, next question says, suppose that Shannon is late for school. That's our given condition. You already know this event has happened. So we already have given that she's late. So suppose that Shannon's late for school. What's the probability that she hit the snooze button? So let's say we see Shannon come in late for class. All right, we know she's late. We're wondering, did she hit the snooze button or not? So we should be able to calculate that. So we have this formula we talked about earlier, which will help us kind of think through this. So the probability of snooze given that late, well, we want to look at all of those late times. Out of all those days where she's late, how many of those was she late and snoozed? Cool, so that's our conditional probability formula. I mixed up A and B there, but that's fine. Okay, so we already found one of these things. We already found the probability of being late and snoozing. All right, we found that right here. That was 18%, 0.18. And probability of being late, we found that as well. That was 0.22. So of all those days that she's late, supposing that she's late for school, we've seen that 0.18 out of the 0.22 total, she hit that snooze button, and that's probably what caused her to be late. All right, so 0.18 divided by 0.22 is 0.82. So if she's late for school, there's an 82% chance that it's because she hit that snooze button. There's an 82% chance that she hit the snooze button. We're not going to assume causality. All right, so we'll stop there for this video, and next time we'll look at the idea of independence, how we can use conditional probabilities to find out if two events are independent or not.